Sometimes, as life may have it, the old ticker doesn't do what it's supposed to do. On occasion, you might see in the national news an individual that is prolonging their life with an artificial heart. Well, where does this come from? Right here in Pennsylvania, we have one of the leading medical research institutes in the world.
Today on Futures Fast Forward, we're going inside the Penn State College of Medicine at the Hershey Medical Center for a look at the people that work together as a team to develop cutting-edge, life-saving technology right here in Pennsylvania.
Well, my role is an engineer aide, so I kind of take the ideas that the engineers in the big offices here think up and design and actually take those and make them into a working product.
This episode of Futures Fast Forward is brought to you by our friends at Miller Welding and Machine Company. Founded in 1963, Miller Welding and Machine Company of Brookville, Pennsylvania is a single-source solution encompassing fabrication, machining, and finishing technologies aimed to meet the wide range of needs that our customers demand. Staffed with a team of engineers and highly skilled employees, our quality and our commitment make us a leader in this industry. We provide our customers with high-quality parts by continually improving the processes we use, and we provide our employees a safe and satisfying work environment and invest in their futures by constantly investing in new technologies. 2 readily accessible state-of-the-art facilities accommodate our workforce of over 300 highly skilled employees. For current news and employment opportunities, visit our website at www.millerwelding.com.
Tell us a little bit about the start of the process and where this program has come from the beginning.
Well, there was nothing in the beginning. Dr. Pierce, who headed the team, was in medical school at Pennsylvania, University of Pennsylvania. The professor challenged him to develop an assist pump for failing hearts. He got out of medical school and after his residency, he went to National Institutes of Health and worked on it with Mr. Jim Donakai. And the two of them together collaborated to the Pierce-Donakai assist pump, which is now owned by Thoratec and developed under their own, called a Thoratec VAD for ventricle assist device. It's the only device in the world that can be used in an assist pump in 4 different configurations. Everything else that exists can only be used in 1 configuration. And the shot in the back shows how it can be used. In standard formation, it's a left ventricle assist device, and it can be hooked up to the atrium or to the left ventricle, which is commonly done on transplantation. It can also be used as a right ventricle assist device or with two devices as a biventricular assist device.
Well, we've come a long way in how patients are managed with these devices, the importance of getting patients up and active, nutrition. There's a lot of basics to getting these patients to do well on these systems. And a lot of that's been learned over many years, some newer drugs that are available now. So there's a long, slow learning curve in this area.
The next step down, of course, would be 2 pumps together, implanted, and that's your Penn State heart, your total artificial heart. The ventricles are exactly the same. The only difference is these go inside the chest and the air lines come out, whereas this pump is outside the chest, called paracorporeal. The cannulas come through the chest wall.
Now the cannulas are the tubes that link or connect the heart, the blood flow from your heart to the assist pump and then back out of the pump to your aorta. So blood flows through these tubes that is being fabricated right here on the sleeve.
The top 2 devices are assist pumps. The bottom are total artificial hearts. These devices over here are pneumatic. These are the new electric motor devices. So we think we're the only institution in the world that's worked on all 4 simultaneously at one time.
There's a lot of medical institutions, Cleveland Clinic, Utah, Louisville, other places that have and are developing, working with industry to develop heart pumps. We are one of the pioneers in this field. We've come out with braking technologies, the first fully implantable device. Dr. Pearson, his first pneumatically driven device, which went on to be the Jarvin.
Wouldn't the pneumatic pump cause, like, because it said it's run by air. When you're mixing air with water, doesn't that kind of, with like the blood or stuff, wouldn't that cause it to bubble and get clogged?
The air side drives the blood sac, pushes the blood sac back and forth, so the air actually doesn't contact the blood.
Now, there's other polyurethane components you can see here, like compliance chambers and stuff. The blood is not actually in them, even though they're in the body. The material is a great type of blood service. It actually is like 25 dynes per square centimeter surface energy. Blood cells seem to last between 20 and 30.
That just, went right over my head. As would be expected, right?
Futures Fast Forward is brought to you in part by Du Bois Business College, providing quality post-secondary education for over a century. Their commitment is to develop programs that enable their graduates to be successful in their field of study. And they work closely with businesses and set programs that correctly mirror current industry trends and the modern use of technology. With 3 campuses in central Pennsylvania, Du Bois Business College can help you touch your future faster. Visit them on the web at dbcollege.com.
Welcome to Jeff Tech, the school of choice. The IT industry is a dynamic entrepreneurial working environment that has a revolutionary impact on our economy and society. IT careers involve the design, development, support, and management of hardware, software, multimedia, and systems integration services. Through interactive media, network systems, information support service, programming, software development, and web page design, and management information systems. Get your career going today at the IT Academy at Jeff Tech, the school of choice.
So pretty much everything that the blood touches, like the blood sacs and cannulas, they're made out of polymer.
Polymer is it's a type of plastic?
It's actually, if you look behind you here, it starts out as a liquid. Okay, it's a liquid in a solvent. It's actually 80% of this is solvent, which when evaporated away leaves the rubbery type of polyurethane. There's a whole science to the polymer technology that's completely separate but yet integrated. So we have to do some research and find out what polymers are the best.
So those are the blood sacs on their first stage, or is that when they're...
Well, that's how we start to make them. They're made on a wax. The white material is a wax. So the wax is poured into a mold, okay? Then the mold is removed, and then the wax forms are dipped into a polymer solution.
Robotically controlled by the computer here. We set the speed up and down. That comes out, is put on the rotisserie to dry. Rotisserie will hold the mandrel. Usually it takes about anywhere from 4 to 6, 7 coats of dipping into the polymer to get the proper thickness.
But when it's kind of like spaghetti in a sauce, spaghetti floating in the sauce. You dip a form in, out comes sauce and spaghetti. You rotate it, the sauce goes away, the spaghetti gets hard, right? Next time you dip it, you get more sauce, new spaghetti. Spaghetti wraps around the old spaghetti, the sauce goes away and on ad infinitum. Until you get up 6 or 7 coats and the part's as thick as you need it.
And then we do that multiple times to get the thickness we want, okay? And then when that's all done, the whole thing is put in an oven and the wax is melted out. Okay? And then you're left with this flexible bladder, okay? The nice thing about it, there's no seams in it. And the inside surface of that is very smooth because of the way we make the wax.
How do you keep it from like causing little bubbles in it? Because you said it dips it in and then it brings it up to dry. How do you keep it from creating bubbles in the material and drips and runs?
We get lucky sometimes. Yield rate, even at the best factories that are totally robotic controlled, have a yield rate of at best 50%. So we're lucky if we get 1 good out of 4 that doesn't have a bubble or some type of flaw in it.
So it's not down to an exact art or science yet.
There is some art and a little bit of science involved, but it's not a perfect, yeah. Considering that a jar a gallon of that polymer costs about $4,000, and about 75–80% of that is solvent that's evaporated away. It's very expensive stuff.
Well, how many blood sacks does it take to create one artificial heart?
That sounds like a bad joke. How many blood sacks does it take?
How many licks does it take?
How many blood sacks does it take to come out with one artificial heart, Shane?
My guess is
Well, I'd ask the professional.
Well,
Touche.
Dude, yeah.
The wit is sharp. I'm bleeding. Give me a Band-Aid, man.
well, in a total artificial heart, there's two. Try and wrench on that. Try and tear it.
That would be an important feature in a blood sac, would it not?
Try to tear that again.
Right.
Try it again. Come on, Shane, put the muscle into that.
You know, this thing is only just flexing like that over millions of cycles, so we look for flaws in the hole edges and things.
You would think that eventually it would heat up enough that it would start to. It wouldn't.
Well, only if you have a fever, you know. Otherwise, it should be 98.6 degrees.
Like, you know how normally whenever you are stretching or flexing something a lot,
Okay.
and then you stop and then you touch it, it's normally warmer. I'm wondering if you said it just sits there and goes like this. Would it build up enough friction on it that it would cause it to heat? And
Not heat, but possibly friction. If the surface isn't the pusher plate that's pushing against it's making contact, if there's some jagged or roughness to that, there's possible that friction over time could cause a hole in this.
Are we ever going to reach a point where the technology is so perfected that somebody that's 40 years old is going to be able to live out the rest of their natural life with an artificial heart in the side of them?
Well, that's been, one of the long-term goals. These are used different ways. Some of them are for short-term use, where you have a patient who needs support for a couple days or weeks or months. Mm-hmm. Those are very different devices, okay? And then you have the needs for much longer-term support.
Now, how big of a staff do you manage here?
We have about 25 people here on staff, so it ranges from faculty members to technicians, machinists, specialists, and
Machinists?
polymer. Yeah, we have machinists next door.
Really?
We work with titanium here and different plastics. Most of it all starts here as far as the motor housings, which they call energy converters, and also the artificial heart. This all starts with a solid piece of titanium. It goes to the lathe first and gets turned. We work pretty close tolerances because we have close bearing fits and electrical components in here.
Tell us a little bit about the process and where we are in the building of the heart process.
Well, like Cliff said, this is the foundation of the device. This is the housing.
This is like the engine block, in a way,
sense,
as an analogy, right?
Yeah. And so any of the components that need to be fabricated, that come out of metal or plastic, we bring a drawing to Cliff. Cliff will mill it, machine it, put it on the lathe, sand it, buff it, I'll grind it, fabricate that part, and get it back to us, and we carry on with our next step of building and refining these devices.
Now, Cliff, tell me a little bit about your background. Did you actually have to have some sort of medical background?
I started in high school in not a VOTEC, but a vocational school in Hershey High. And I started here in March the 11th of 1985. I worked part-time. June the 18th of 1990, I went on full-time, and I've been on full-time to the present time.
And you're saying that you're not just working with metals, or titanium in this case, but plastics as well. Now, what are we looking at here, Cliff?
These are connectors.
So you make these devices out of a solid hunk of titanium.
Oh, yes.
That's amazing.
This is a guide shaft. This is stainless. This is 440C. That gets roughed out approximately 20 thousandths oversized, and it gets sent out and gets heat treated. Then when it comes back, then we grind it. That's a part that goes in electric motor that you see there. These are two different, there's a left and a right. We also made a small total unit also, which is what these were for. These are a left and a right. This is a smaller pump. This is a 50 cc. This is for a person up to about 155 pounds.
What are we looking at here?
Give them an example here of part of the process. So what Cliff was doing on the mill here, can I take this out?
Yeah, sure.
Machining the bare titanium housing that will house the energy converter or motor to drive the pump. This is the first step, and over here what we have done is taken that bare housing, installed bearings, the motor, which has a roller screw fixture, secured that, the guide shaft, which
Is right here,
the guide
right?
shaft would fit in here, attached to the pusher plate.
In here?
There's the electronics wired to this motor with a Hall switch. That's all comes to a hermetically sealed connector, which is taped up right now.
My goodness.
So there's a lot of fine work that goes into building this.
Now, Shane, does this surprise you to walk into a world-class medical facility? We're going to take a look at how they make artificial hearts, and looks like Daddy-O's shop back in the garage.
Actually a basement, but yeah. pretty much.
Isn't it? That kind of surprised me as well.
I noticed a lot of these materials, a lot of the machines here, we also have at Tech.
Yeah.
Like, there's the drill press, the lathe, and you got a bunch of other stuff.
That's one of the beauties about this show. You know, you can really.
You have better equipment.
Go ahead. Say that again?
I said you probably have some better equipment at your Votech with probably have a CNC mill machine.
Yeah, we do.
have a laser engraver too.
Let me ask you a question. Is your father's name Daddy-O?
No, it's Carl.
Okay, so I guess you kind of misquoted the name.
Yeah, for all you hipsters out there.
Futures Fast Forward is sponsored in part by United Electric Cooperative. United Electric is special because it's owned by its members and is guided by a set of principles that reflect the best interest of those members. United Electric Cooperative members reside within 10 counties in PA, and the cooperative operates an electrical system that spans 7,000 square miles while employing 72 local people. United Electric Cooperative, owned by those we serve. Visit our website for updated job opportunities. Jefferson County, Pennsylvania is open for business with excellent tax-free building sites, a talented and experienced workforce, and business services specialized for your development needs. Jefferson County Department of Economic Development is ready to help you and your company grow and prosper. Join other prosperous companies such as Miller Welding and Brookville Equipment that have made Jefferson County their home. For more information, contact the Jefferson County Department of Development.
But are you guys actually building the hearts? You making
This is the heart factory right here.
Really? Literally putting it. This ain't like rebuilding your four-wheeler, Shane. It's a little bit more complicated than that.
So my name is Branka Lukic, and I'm a senior research assistant in artificial heart laboratory. I specialize in performing hemolysis experiments, which is testing the blood pumps, how well they perform with blood environment.
Explain to us what's happening here. So we have an item that is coming to you for testing for what purpose?
Well, first of all, let me tell you, all the blood devices, all the devices that go into someone's body first need to be tested in vitro, which is in a laboratory settings, and then they're tested in vivo. And after that, they go to clinical trials. So we do different kind of in vitro testing in the laboratory. For the dynamic performance, pressures and flows, and for blood performance. Two kinds of pumps, pulsatile pumps and continuous.
The pulsatile pumps are a pump that would have a pulse to them,
Yes,
like
exactly.
your heart.
They're similar to what your heart is doing. They For example, this is the arterial line pressure, and it looks similar to what you would have in a human body. This is the drive line, and the air goes in and out and pushes the diaphragm that pushes to the blood sac and ejects, like
Right.
in this case it's saline, and in actual body it's blood.
Right.
And inside of this device here are valves that are opening and closing, and they're providing unidirectional flow. When they're opening and closing, there are some forces associated with that closure part and the opening as well. These forces can destroy blood cells. The easiest way to evaluate that destruction is to measure red blood cell destruction, which is called hemolysis. And every half an hour we take samples of blood and we send it for analysis and measure plasma hemoglobin.
So you have a device on here for how long?
Well, I've been testing this pump for a year and a half now.
This big blue unit is what we use to power the air-driven pumps, which this latest 12cc pneumatic pump is an air-driven pneumatic pump. The whole unit has now been replaced with the electric units that we'll see over here, and is totally implantable. So it went from something this size to something this size.
Wow.
By going to electric instead of air drive. This is what we call a mock loop, or performance testing loop, that we test the devices on before they go ahead and get implanted. Monitoring software, the actual device itself here, this is the Arrow Lion Art that was developed here at Penn State and then produced by Arrow International, who is based out of Reading, Pennsylvania. They were making these devices for clinical trials and use. This would all be implanted under the skin. This is the inlet that would connect to your left ventricle, flows into the pump. The blood sac is then squeezed by an electric motor pushing a pusher plate against the sac, and the blood is ejected out into the aorta. This pump can pump up to 7 liters or more a minute. The battery pack will allow you up to 30 minutes of being totally free of any wires, allow you to shower or take a swim without being connected to anything. The energy to this is transmitted across the skin by the transcutaneous electrical PETs. The energy is transferred through the skin. There's no wires going in and out of your skin.
On first impression, you might be tempted to think that a guy like Brad has to have at least a 4-year degree to be able to work in a lab like this, but his formal degree is actually an associate's in electronics engineering from Penn Tech College. He receives certification opportunities and continued training on the job.
So after coating this several times with the polymer, this will be taken off of that highly polished mandrel, cleaned, prepped.
In regards to the on-the-job training, you didn't learn how to operate a medical lathe in electronics school.
Right.
Right. Okay. So that's what we're talking about.
Yeah. A good foundation and mechanical ability, as well as critical thinking, able to think things through in processes like this. Because not only are we making these, but we're developing and writing a whole process, a procedure in writing as we do it, and have to document every step of the way what is being done, what are we using, time, temperature, humidity, all kinds of different parameters that all have to be met and followed.
Are the engineers establishing that lab model for you, or do you have leeway in your career to be able to help hone the process yourself?
Yes, being that this is a research institution, it's not really the heart factory, but it's more so research and development. So it's ongoing. If we find a flaw, which I did just a few months ago, I found looking under a microscope that the mandrels we're using to make these cannulas weren't as smooth as we thought they were. They had little tiny scratches or pits, and to a blood cell, it's the difference between rolling a bowling ball down a bowling alley or rolling it down the street. Okay, it's a totally different surface for the blood cells, and we want to keep those blood cells nice and happy and thinking that they're in an organic blood vessel, not something artificial.
So the body doesn't reject it.
Right, exactly. So that's the whole point of a lot of this research, is to make blood-friendly materials. Well, again, that's one part of it. The other part is all the other mechanical engineering aspects of making a pump, a blood pump itself. But setting in, Loctiting in bearings, measuring all the tolerances. There's a little circuit board that needs wired in the electric assist pumps. Insulating them, hermetic connectors, all the way built up, and then putting on a mock loop and testing, performance testing device after it's been built. This is an inspection station. We have a light microscope here, a 40x microscope. As I like to tell people, this is the only job I know of where your work is inspected under a microscope.
Yeah.
Because we actually literally do take every component, look at it under here, look for flaws, look for defects under 40x magnification.
Just a visible inspection.
Yes. We have a photographic station where we can mount a camera on here.
Oh, cool.
Take picture evidence of what we've done or what we've seen coming post-explant of a case, where we can open it up, look at problem areas, document them, and try and make improvements.
What is all this?
Well, the stir, hot plate, pretty standard lab equipment right here. This device measures the percent solids of that polymer. Like I said, it was suspended in a solvent solution. We put a little sample on here, and it weighs it. It evaporates that solvent, and what we're left with is just the polymer, and it gives us that percentage weight. So it'll give us the percent solids of polymer. This little device
Looks like a bolt.
is an ultrasonic thickness gauge. This pressed up to a blood sac. Let me grab that one right there on top of that notepad. Yep. So we can tell, using this ultrasonic thickness gauge, how thick that is in different areas. There's a certain spec that these need to be. We have a viscometer, which measures viscosity of liquid, a little grinder here, and we can grind small parts as we need them. Another thickness gauge. This comes out to be 14 thousandths of an inch thick, for example. Magnetic thickness gauge there that uses a ball and measures the thickness between that ball and the magnetic coupler. Kind of a double check to the ultrasonic way of doing it.
Now, a lot of these devices that we're looking at, Brad, these are things that are pretty standard electronics diagnostic tools that you would have used in your electronics education.
That's one of my duties as well, not only to use these things, but to calibrate these things, make sure they're giving us the correct readings.
Now, what advice would you have for somebody that's looking at getting into a career at this point, whether it's going back to school or just starting out at high school?
Just get as much education as you can while you can, because it's much tougher once you start working full-time to get formal education. Of course, I've learned a heck of a lot more on the job since I've gotten out of technical school, but having that as a foundation to build upon was key.